Hi, I'm Lawrence Krauss, and I'm very happy to have the opportunity to talk to you briefly today about my new book, The Physics of Climate Change, which had its origins in a variety of current crises, as I'll describe, in fact. The motivation for the book began when I led a small travel excursion to the Mekong Delta to explore the culture, society, and geography of that region earlier this year. And in preparation for that voyage on a riverboat, I prepared a few lectures on climate change, which seemed relevant at the time for the Mekong Delta. I had no idea, I think, when I first prepared them, how relevant the Mekong Delta was. As you'll see, my new book begins and ends there, because in some sense, the Mekong Delta is a perfect storm for climate change because of a variety of factors that may affect it in the near term. Climate change is occurring and will continue to occur, human-induced climate change, over the next century or two or three or four or more, depending upon what human civilization does. But even in the next 30 or 40 years, the effects will make themselves evident in a few places around the world, and the Mekong Delta is one such place. When I spoke about this, I was somewhat depressed to be able to take this group of people on a beautiful, beautiful riverboat and talk about something that seemed, in principle, depressing. But this group of well-meaning travelers who were interested in science as well as culture were incredibly interested in learning about the basic science of climate change, something that I think it gets overlooked too often in the emotions of the issue. And what I wanted to do was prepare a discussion which would, for any layperson, would help them understand the basic science of climate change, enough to give them a perspective to understand what they see in the news, and to also to appreciate what predictions are rigorous and what predictions are more speculative. And I decided to do that, and then decided to write this up as a book in part because of the reaction of the audience on the ship. But another factor came into play here, and that was the worldwide pandemic. I found myself earlier this year having to cancel 7 trips and many other activities that were ongoing, and was at home. And I tried to think of what I could do here for the world. I'm not a first-line responder. What could I do for people? And I prepared some physics videos, but I thought, why not try and write a book on this subject? And I did what I've never done in now 11 books. Because I was completely both isolated and all of my outside activities were curtailed, in 12 weeks I was able to write a book that would normally have taken me at least a year. The researching, of course, I've had years of preparation by dealing with colleagues at the Bolton Atomic Scientists and other colleagues in the School of Earth and Space Exploration, where I used to teach, and who've tutored me for many years. So I had a head start. But it was fascinating for me to learn about the subject and to really realize how far back the basic science goes, and how really fundamental and simple it is in some really important ways. People have the impression that to understand global climate change, you need supercomputer models and complex numerical algorithms. And of course, to understand the details of climate and make specific predictions about what climate changes may happen in various locations, you may need that. But to understand the basic science, the energy flow of the Earth, really the Earth's climate comes from the fact that the sun is illuminating the Earth with radiation each day, and the Earth is radiating energy back into space. And when the radiation going out equals the radiation coming in, then an energy equilibrium is established, and a balance is made. When more energy is coming in than going out, then the Earth can heat up, and vice versa in the other case. And what I realized in the course of my own studies was some fascinating facts, one of which goes back almost 150 years or so, slightly more than 150 years, back to Arvid Högborn, a Swedish geoscientist, who actually advised Svante Arrhenius, who's probably known as the father of climate change in some sense, or at least what's become known as the greenhouse effect, one of the first Swedish Nobel Prize winners. In the end of the 1800s, early 1900s, he discussed the impact of carbon dioxide on climate, but he actually borrowed heavily from the work of Arvid Högborn, who did an interesting calculation, the kind of calculation I love as a scientist. It's a black of the envelope calculation. He asked himself whether human civilization or life in general could impact on the atmosphere. It seems daunting to think when you think of the atmosphere that we could have any impact on it. But he looked at the time at the estimated amount of carbon dioxide in the atmosphere, which you could estimate reasonably at that time, and realized he did a simple calculation. Said, if say you take all the carbon and the carbon dioxide in the atmosphere back in 1900 or in the 1860s when he first did this, take all of that and turn it into liquid or solid carbon. How big a layer on the surface of the Earth would that take to account for all the carbon in the atmosphere today or at that time? And the result is quite surprising. It's a layer 1 millimeter thick of carbon. And when he argued about living systems on all the continents on Earth, he said, well, it's clear that life itself could certainly impact on with that amount of carbon. And he made the first estimate that perhaps human industrial activity might input carbon dioxide in the atmosphere. Then there's another interesting result, which is perhaps surprising, which actually I learned from my friend Lord Martin Rees, another physicist, an astrophysicist, who was kind enough to comment on the book and have discussions with me. And he pointed out something which is interesting. A lot of people think, well, how could carbon, which is 4 parts in 10,000 of the atmosphere, affect climate? Something that's such a small percentage of the atmosphere. And he suggested a simple test what you can do to see that small things can have a huge effect. I can block out the sun completely on a sunny day by taking a single piece of paper and blocking out the sun. But this single piece of paper is a very small amount of material compared to the atmosphere above my body. In fact, it's less than 1 part in 1,000 if you consider that the pressure where I'm standing right now is 15 pounds per square inch in the sets of units we use in the United States. If you consider that basically there's 15 pounds per square inch of atmosphere above me causing that pressure, then the amount of material in this piece of paper is less than 1 part in 100,000 of the atmosphere. But nevertheless, that small piece of paper can block out the entire sun, which otherwise comes through the atmosphere to me. So there's some non-intuitive aspects of climate change that are important. And the other aspect of climate change, which I think is particularly important and perhaps not understood, is that really the dynamics of carbon, of what's called radiative forcing, which is really the effects of increasing carbon dioxide in the atmosphere on the temperature of the Earth, is that the real important stuff doesn't just happen at the Earth's surface. Actually, what governs what ultimately is a temperature at the Earth's surface in the atmosphere comes from the fact that the Earth, as I say, is radiating into space. And if it's radiating the same amount of energy out into space that it's receiving from the sun, then you're in equilibrium. But what happens as you increase the carbon dioxide abundance in the atmosphere? Sunlight, which comes to the Earth in visible and ultraviolet wavelengths, many of which the atmosphere is transparent, comes down to Earth. And the Earth, of course, is radiating a much cooler temperature than the sun. And therefore, it's radiating that energy back in infrared radiation. And water and carbon dioxide absorb infrared radiation. And so if you increase the carbon dioxide abundance in the atmosphere, what happens is, well, the atmosphere becomes opaque to that radiation until you get to the very surface of the atmosphere, high up, 40 or 50 kilometers perhaps up above the surface of the Earth, and or maybe a little less, and that governs the equilibrium of the Earth's energy balance. Because what happens is, if if you're absorbing more carbon dioxide in the atmosphere doesn't become transparent and radiate into space until higher up, at a higher altitude. But when it's higher up, it's colder. And since the amount of energy that the Earth can radiate goes as the fourth power of the temperature of the surface at which it's radiating, if you're radiating from a colder surface, you're radiating less energy into space. And that means if you're receiving the same abundance as you were before of sunlight, but you're now radiating slightly less energy because you're absorbing more of it down here and you're radiating from a higher surface, that means there's a net energy flow in, and that's called radiative forcing. And if we can calculate that, it's a simple calculation. We can actually measure it too with satellites. Looking down at the Earth and up above, up at space, we can measure the relative amounts of radiation coming in and out to check that energy balance. And we find that there's a certain power, a certain watts per square centimeter of excess energy that's being absorbed because of the increase in carbon dioxide. And then we can use some very simple physics to estimate what impact that has on temperature of the Earth. And even though, as I say, one needs sophisticated computer models to get the details exactly right, it's amazing how some very simple physics give you the right order. You can estimate that given the amount of increased carbon dioxide in the atmosphere, which has changed by 30% in the last 70 years or so, 30% increase in the atmosphere, you can estimate that the temperature of the atmosphere would have gone up at the surface of the Earth by about 1 degree Celsius, which is what's happened. And so basic principles agree with observations, and we understand the physical mechanisms. Now, of more concern, perhaps, are what are the implications of that temperature change? And I discussed the physics of that, but there's one aspect that's particularly interesting. We talk about sea level rise, and many people think sea level rise is related to the melting of glaciers or the melting of the glaciers in Greenland or in Antarctica. And of course, that does contribute a little bit to sea level rise. But what's much more fundamental and in fact more interesting for those people who are worried about modeling the future is, in fact, we've already put that energy in. If you consider the additional heat input in the Earth in the last 60 years, it's gone in the oceans, and it takes a while for that heat to equilibrate. But one of the very simple properties of water is that as if you heat it up, it expands. And just from the heat that we've already put in, even if we stop burning fossil fuels today, you can show that over the period of the next 50 years or so to the next century, the water will expand just to do that equalization of heat throughout the oceans by about 1/3 of a meter. So sea level rise is already built in 1/3 of a meter, independent of any future models or anything else. Now, is that going to end life as we know it? No, but it will have an impact, as I talk about. In fact, an impact, as I describe, in the Mekong Delta and other places where we discovered the average elevation of that landform is lower than we thought above sea level. There are more speculative predictions about what might happen from in the long term over the next century or millennia. And we can again look at paleogeology to try and get estimates of what have happened in the past in terms of sea level rise, temperature of the Earth, etc. And I talk about that. But as I say, one of the things I try and do in the book is present the data, present the basic physics, present those predictions which are clear, unambiguous, and in some sense written in stone, and also the level to which other predictions are more speculative, so that you, the reader, can decide how urgently you this global problem, and hopefully have the perspective to decide how to vote for politicians and review policies that they might make. This book is therefore for people of all political persuasions, left, right, center, and I hope people will view it that way. There's no political agenda. This is just science. Well, those are some of the things I talk about in the book. There's a lot more, and I believe along with this there'll be a small excerpt from my book and some quotes. And I hope it intrigues you enough to consider getting the book, which comes out January 26th in the United States and February 4th. In England and Australia and other English-speaking countries, and in several translations around the world. Thanks again for listening, and I hope if you have a chance that you enjoy the book as well. Take care.